Hello, everyone. Hope you're all doing well. So, we kind of said at the very beginning of this note packet that we were going to end up using our models for two kind of overall goals. The first was prediction, which we've already covered, and the second is going to be to say something about what the overall population mean is from the data that we collect in our sample. So we're going to put a pause on the first year GPA example for a brief moment, though we will come back to this eventually. And we're going to go back to this US Census data example. And so when we're talking about this sampling distribution of the sample mean, remember when we discussed the sampling distribution of the sample proportion, we used this US Census data where we talked about the sampling distribution for the proportion of US households that have a pet. And so the sampling distribution of the sample mean is going to look extremely similar. So if this kind of made sense to you like a month ago when we were doing this for the sample proportion, it should make sense now as well because not much is going to change. If we want the sampling distribution of the sample mean for, say, average income, for a sample size of 100 households, the steps that we would use to make this are we would just take a sample of 100 households and find the sample mean income. We would then take another sample of 100 households, finding the sample mean income. So there's this idea of repeated sampling coming up again, and we would end up repeating a large number of times. So we're thinking on the order of maybe millions. So calculating millions of sample mean incomes. When we introduced this idea before for proportions, we used StatKey and we did a whole kind of deal with looking at a simulation and looking at what the distribution looked like. We're not going to do this for the sample mean, but I just wanted to point out that we could do this. So, right, we could use StatKey to kind of do this type of simulation and then look at what the sampling distribution would look like for a sample size of 100. For a sample size of 10, this is just going to have the same steps, but now we're only going to sample 10 houses at a time instead of 100 houses at a time. And we also talked about this idea before that if we take a larger sample size at a time, so if we sample 100 households, then that sampling distribution is going to have a smaller spread. And we saw that in the app kind of messing around with different sample sizes when we looked at the sample proportion. So the same idea holds for the sample mean. The sampling distribution with the larger spread is going to be the sampling distribution when our sample size is 10. Okay. And so again, we're going to end up using this sampling distribution eventually to make a confidence interval for the mean and to conduct a hypothesis test for the mean. So the sampling distribution is pretty theoretical. It's nothing you would ever actually generate in real life because you don't have the time or resources to sample millions of times. It just doesn't make any sense. But it's going to be useful for our confidence interval, and it's going to be useful for our hypothesis test. And so just like we had for the proportion, we're going to have a central limit theorem for means as well. And so if our sample size is large enough, then our sampling distribution of the sample mean will be, and so for proportions, if the sample size was large enough, then that sampling distribution was going to be approximately normal. It's the same deal for means. So it's going to be approximately normal with mean, so it's going to be centered at the population mean. And it's going to have a standard deviation equal to that, where it's been a while since we looked at that notation, but this little kind of O with the little tail hanging off, we're calling that sigma, and that is the population standard deviation. And N is just our usual sample size. And so that central limit theorem just said that, okay, if the sample size is large, and we're also going to add an independence condition just like we did before, then that sampling distribution is going to be normally distributed. But what does kind of large really mean? We had that success failure condition for the proportion case where we were checking if n times p was bigger than 10 and n times 1 minus p is bigger than 10. For means, we're going to have a slightly different condition. And so for condition 1, this one's the same. We still assume that our observations are independent. We've kind of thought about this as each observation is providing completely new information. Condition 2, this is going to be similar to our sample size condition that we had for the sample proportion. And so we're going to say that the sampling distribution is going to be approximately normal if this independence condition holds and one of the following is true. So either we have a small sample size, so n less than or equal to 30, and there is little skewness and no clear outliers in our data. So if our sample size is small, then we're going to have to see that there's really little skewness and that there's no clear outliers in our histogram or box plot. Or if we have a large sample size, then we're going to say we're good as long as there's no extreme skewness and no extreme outliers. So both of these are somewhat subjective conditions that we'll get a little bit of practice with once we move into some real data examples. As always, let me know if you have any questions. Where we're headed next is we're going to spend a little bit of time just introducing this t-distribution, and then we're going to jump straight into the confidence interval and hypothesis test for the mean.